Okay. I'm going to give you guys a quiz tomorrow. I'm going to ask you to graph the sine function, the cosine function, the tangent function, the secant, the cosecant, and cotangent. Those 6 things. Okay. It's going to be a short quiz. It shouldn't take us very long. Okay. But I want to give you a strategy in case you get stuck on remembering what maybe a parent function point was or something like that. You can always reference the unit circle to get back to a set of ordered pairs. Remember that when we are graphing, for instance, the sine function, okay, that's what's going to graph over here first. So if I graph the sine function, I'll just call it f of x equals sine of x. Our ordered pairs are an x comma y, but this x is actually theta or t from the unit circle, right? And this is then the y value, because I'm doing a sine, this is the y value from the unit circle. Is that okay with everybody? Okay. So, if we keep that in mind, as I move this point A around, we're going to see that behavior here, okay? So you see right now that this x is that radian. It's 0.57 radians. Does that make sense, everybody? Okay. This y value here is that y value off of that point on the unit circle. Okay. So we're seeing here we are radians, or I guess our theta or t, comma, the y value from the unit circle. All right. And then if you move to there, it's the same thing. So we see then that we're going off the radians of 1.05, comma, then that y value off the unit circle. Okay. So which ones are really nice ones to use for the sine function? Well, that one's really nice because now we're plotting 0 radians right there, comma, that y value. So that's a really nice ordered pair, right? Okay. Some other nice ones as we move through here end up being that one, right? Because now we should be able to find pi over 2 on this x-axis pretty easily, and that's what that number right there is. So pi over 2, comma, the y value off the unit circle, which is a 1, which that should be a really easy point to plot as well, right? Okay. And we keep doing that all the way through. Now, we would want to normally plot those points there, okay? But usually we're just going to plot that one right there. So right now, as we're doing this, we would have just plotted that one, and plotted that one, and plotted that one. And then we know, well, as that value of, as that point A travels through there, okay, if we plotted those correctly, we should be able to get the rest of those points kind of positioned right. Does that make sense? Okay. And then another one would be pi over 2, or sorry, 3 pi over 2, 3 pi over 2. So it gives me that point right there where my cursor is. And then we'll kind of finish back up at 2 pi, comma, 0. All right, and that's what's developing the unit circle. So these red points are the points that we're going to want to plot initially, but they come straight from the unit circle. So if you get stuck on any of these 6 curves tomorrow, generate a unit circle. You don't have to have all 17 points off the unit circle. There we'll only use, what, 4 points off the unit circle? Okay. One of them was redundant, 0, 2 pi, it's kind of redundant, but if you can do that, you can graph the sine function. Okay. The cosine function then, so that's my radians, the way I've got this programmed in GeoGebra, that's my radians. This is the y value off the unit circle. Cosine is what value off the unit circle? The x. So I'll plot that, see what that looks like. All right, so I get down here, and you see right now that before we even start moving this point A around, 0 radians, and then the x value of point A. Well, 0, 1 is that point then. And as I start moving, okay, you see that 0.28 radians and then the x value of 0.96 off the unit circle. Now, those are ugly values to plot, so we would never really plot those. We would, again, would come up here and plot that point because that's really easy. 0.157 or 1.57 is pi over 2 radians. And then plot the x value against that. So pi over 2, comma, 0, and we would plot that point right there. The next point that you would plot would be over here at pi, and the x value there is -1. So we'd have pi, comma, -1, and you see it, that's what that's giving me right here, z. Okay. Keep going through. I get 3 pi over 2. It's 3 pi over 2. The x value associated with that blue point then is 0, so that becomes the y value over here. And then we'll get back up to 2 pi eventually. Okay. So that is how we get our cosine function. Is that all right with everybody? So the main issues that I've been seeing people have is, well, then how do I get the tangent? How do I get the cotangent? Where do those asymptotes come from and all that kind of stuff? So if I look at z, okay, I'm still going to go radian as my x value, but now for the tangent is sine divided by cosine, right? Or y off the unit circle divided by x off the unit circle. Okay, so when you graph the tangent function, tangent, my input is our radians. My output, okay, is going to be the y divided by that x, okay, off the unit circle. So, again, theta, or if you want to call it t again, and those come from the measurements off the unit circle, and then this ordered pair is the y divided by the x off the unit circle for those radians, or and they're both radians, but that angle or that distance. Okay, and remember we talked about those being the same ultimately. So some nice ones to think about. Okay, if I'm looking at this right now for the tangent function, obviously the radians is 0, so that's where that ordered pair, that coordinate is coming from. And then if I divide y by x, I take 0 divided by 1, I get 0, right? So that's where that ordered pair is coming from. Now, as I go through this, and I'm just going to put just a reference point for me here to stop point A. Square root of 2 comma square root 2. All right, so I start moving around here, and I get to that point right there, okay? And we see that that's 0.78 radians, or pi over 4 radians, right? Does that make sense, everybody? So that pi over 4, okay, is the x-coordinate here. And if I divide those two things, what do I get if I divide those two things, y and x? I get 1. So that's why we have the point pi over 4, comma 1. Okay. Some other nice points are this one here. Okay. Now, why does this thing look like it tended off to infinity? It's because when I'm at this point here at pi over 2, where I'm at radians of pi over 2, I'm going to have y divided by x. What's 1 divided by 0? Undefined. So we have an asymptote right there. Okay? Keep moving, and you start to see, you know, we'll get to eventually 3 pi over 4, which is about right there. Okay? At 3 pi over 4, which would be that number right there, you have radical 2 over 2 divided by negative radical 2 over 2, and that's why that y value becomes -1. Keep moving along. We divide these two. 0 divided by -1. What's 0 divided by -1? It's that 0 right there. Keep going along here. You should get another, where'd it go? At that point right there, I got a negative divided by a negative. What's a negative divided by a negative? a positive, and because of the same values, same quantities, we get that 1, okay? And this here would be, what, 5 pi over 4, okay? I would go along to 3 pi over 2, and I'm going to take this y value divided by that x. Negative 1 divided by 0 gives me undefined. So at 3 pi over 2, I have another asymptote. X equals, okay? And then we'll finish off and get that, okay? Now, generally speaking, a lot of times when we graph the parent function of tangent, we don't necessarily look at this interval here. We usually like to look at this one here, right? Okay, between negative pi over 2 and pi over 2. But you can start to get the visual of the fact that if we look at that curve right there, it is that portion, right? And because these things repeat themselves, this portion here is going to be that portion. So if these things are going to repeat themselves, shouldn't this over here kind of be that same thing? Does that make sense, everybody? And you should have then another asymptote, negative pi over 2. But the way that that other asymptote at negative pi over 2 shows up is the logic that, and I can't do it the way I set this up. It's going to haphazardly set this up first period. To get this portion of the curve down here, it's when we move around the unit circle in a clockwise direction, okay? And you start to see at that point Z is now moving kind of clockwise, right? Starting from the upper right and starting up here, and it's going to go down. Well, once it gets here, just the way I got it set up, it regenerates, comes back over here, but it should continue down here through this quadrant. Is that all right, everybody? So that's the tangent. Now, if I wanted the cotangent, how do you develop the cotangent? Well, the cotangent then, let's just call it T. So that's that arc that we're tracing out in the unit circles, T. That is x divided by y, because it's the reciprocal of tangent, right? Tangent was y divided by x. Cotangent is x divided by y. So now we're taking these values and dividing them x by y, okay? So let's see if we can do that. We have x divided by y. Okay, so I'll start here at 0. Okay, so if I did x divided by y for cotangent, what is 1 divided by 0? Undefined. So here we have an asymptote at 0. Okay, now I start moving this thing around. Some really nice values to deal with again is that one right there. Okay, x divided by y would give me 1, right? So at pi over 4, right here, that x value of pi over 4, you see it, you plot it against a y value of 1, okay? Because it's this quotient, okay? Another nice one would be here. What's 0 divided by 1? 0. So at pi over 2, we get that y value of 0, okay? Okay, so keep going through. We get over here to pi. Okay, and now I get x divided by 0 again. X divided by 0. What's negative 1 divided by 0? Undefined. So again, at x equals pi, we have another asymptote. We can keep going through. We see that it starts repeating itself. Right there again, we have 0 divided by negative 1, which is just 0. And up here, we would get 1 divided by 0, which is another asymptote, right? Okay, and that's the cotangent. But the key thing to know on the cotangent is at that point right there, pi over 4 comma 1. This point right here, 3 pi over 4 comma negative 1. Okay, asymptote at pi, asymptote at 0. Okay, and I find that students that can understand that process, that understand if they get stuck with a point not sure about it, or they get confused, because there's a lot of asymptotes in these functions. 4 of them have asymptotes, right? Tangent, cotangent, secant, cosecant. If you get stuck, you can look at your unit circle and say, okay, what was the cotangent? What do we call that? What order of division do we do? Okay, well, it's x divided by y. So where at on the unit circle do I have division by 0? And that should then tell you where your asymptotes are. Is that all right? And it's the same thing for tangent, same thing for secant and cosecant. Let's do cosecant. Cosecant is the reciprocal of what? Sine. Okay? So that is the y value, correct? I just want to bring z back in so I can see it real quick. All right, so if we're doing the reciprocal, how would I, if this is the y value right here, how do I type in the reciprocal? 1 over that, good. Okay. So now when I get down here, okay, we're still plotting over here, so we're going to do the cosecant, okay. That is going to be, it's essentially, it's 1 over your sine, or 1 over the y value, right? Well, if I put that y value, 1 over that y value right there, what do you get? Undefined. So we have an asymptote right here. Okay? As I start moving this thing around, okay, I'm going to get to, let's get to a nice point here. I don't know if I can get exactly to it. Get close. Okay, so z right now is like right there. Okay, because this is pi over 6. Oh, sorry. This is pi over 6. Okay, so we're seeing pi over 6 here. What is the y value for pi over 6? It's 1/2, isn't it? Now, I can't get to 0.5 here. But if it's 1/2, what's the reciprocal of 1/2? 2. That should ultimately be a 2. Does that make sense, everybody? Okay. And now I don't know if I zoom in, if I can get there a little bit easier, a little bit better. There we go. So there's my 0.53 pi over 6. So we create that because of rounding, that would be 2. Okay. But I can keep moving around this unit circle. I get here, okay? Come on. Okay? What is the reciprocal of 1? 1. And that's why at pi over 2, we're plotting 1 over 1 right here. Okay? Keep going. Here at pi, okay, the reciprocal of 0. So 0, when we have this 0, and we're going to think about it as 0 over 1, but it could be 0 over any number. When I find the reciprocal of that, when I put 1 over 0 over 1, okay, if I do that multiplication, I now have that, which is 1 over 0. Can I have 1 over 0? No. Okay, so that's why there's another asymptote here at pi. Okay, so keep passing through, and you end up with that other kind of branch of your cosecant curve. Okay, and if we remember, that then mimics some relationships that exist on the sine, right? Okay, and that's why we said when we do the sine function, if we were to graph the sine function and find the x-intercepts are where my asymptotes are, because that's where we have division by 0 for that y value, 1 over 0. 1 over a y value of 0, 1 over a y value of 0, 1 over a y value of 0. Those are undefined values. Is that okay with everybody? Just to save time, I'm not going to do the cosecant, but the cosecant would be the same, or sorry, the secant. The secant would be the same process, but starting with the cosine. You good with that? Okay. So those are some things to think about if you get stuck tomorrow, if you can't remember how to develop those parent functions. Let's talk about I'll do it here. if we think about the sine function, okay, the sine function, it's that graph right there, correct? If I ask to put in a vertical line, okay, does this thing pass the vertical line test? Yes, okay, and it has to because we're calling it the sine function, right? So it must pass the vertical line test because that's what you have to pass to become a function. But if I ask it this, if I say, does it fail the horizontal line test? Yeah, and it fails it a lot, right? Okay, and it actually never passes it. You think maybe it passes up there, but that's kind of the place where it have the least amount of intersections, but it still intersects an infinite number of times, right? So we fail the horizontal line test all the time there. So that's a problem for us because we're interested in inverse relationships. We're interested in, can we have something that kind of undoes the sine function like we have with like the x squared and square root, right? They undo each other. But let's draw a comparison back to x squared and square roots. If I look at x squared, does that thing pass the vertical line test? It is a function, right? Does it pass the horizontal line test? No. It passes it one time at the vertex, but everywhere else it fails. But we said it did have an inverse. What did we have to do to that curve so that it did have an inverse? We got to cut it in half, didn't we? If we look at that portion of it, that does have an inverse. And its inverse then looks like that, right? Is that orange curve the reflection across the line y equals x of the blue one? Okay? So we've talked about this stuff, right? So do you think we can do a similar thing with that curve? Can we maybe restrict that curve's domain to come up with an inverse, a potential inverse, okay? And here's what we're going to do this, okay? We're going to start around the origin. We're going to try to find basically a place around the origin where this graph is just increasing or just decreasing, okay? Because if it starts doing both, and think about, you know, if we just, I'm going to overlay x squared again, okay? If I look at y equals x squared, that thing is doing both, right? As I move from left to right, it's decreasing until I get to 0, 0, and then it starts increasing, right? Because it was decreasing and then eventually increasing, we start to pass through old y values that we've already hit. Does that make sense? Okay. So in order to eliminate that, what we do is we eliminate the situation of having both features increasing and decreasing on the same curve. So we cut this thing right down. We basically find the minimum. We cut right down that axis, get rid of half that curve, and now it's only increasing, right? Does that make sense? Okay. So can we do that with the sine function? Can we look at this thing and realize that, you know, if I start at negative 2 pi, I start increasing, and then I start decreasing, and I get all the way to negative pi or 2, and I start increasing again, I get to pi over 2, and I start decreasing again, okay? If I look at just that right there, would you agree that version of the graph, that portion of the graph is just increasing? Okay? But once I get over here, it starts to decrease, right? So any one of these dotted points would be a y value that we've already passed through over here, so we would fail the horizontal line test if we incorporated these dotted points with these solid ones, right? So let's not incorporate those. Okay? But for the same reason, am I still increasing if I go from here to there? Okay? And are any of these y values repeated in what I've already got written up here? No. Do I want to go beyond that direction? If I go that direction, do I fail the horizontal line test again? Yeah. So I don't want to include those dotted points. These are the only points that I want to include on my restricted sine function so that it has an inverse. Okay? So what we're going to do is we're going to look at sine of x between x values of what x value? What would be my first x value? Negative pi over 2. And my last x value would be pi over 2. So we're just going to look at that thing. Let me hide this. We're looking at just that curve there. Okay. Now, on that curve, we have points like, let's see if this will work. We have, our pi over 4. It's not going to do it the way I want it to. Comma, square root of 2 over 2. No, doesn't work. We have that point right there, right? Okay. I'm just going to label it as pi over 4 root 2 over 2. We have, and we have a lot of these. We have, pi over 6, comma 1/2 is on there. Pi over 6, 1/2. We have pi over 2, comma 1. We have pi over 3, comma square root of 3 over 2, right? We got 0, 0. Those are all points off of the sine function, right? And we can do that in that third quadrant as well with negative radians, okay? And then obviously the y value would be negative as well. But those are key points off of the sine curve. Right now what we have here is the sine of x, okay? But we've restricted it between negative pi over 2 and pi over 2, and we'll just make it equal. So we restricted it. We restricted the domain. We said these are the only x values you're allowed to use. So we're going to say our domain is negative pi over 2 to pi over 2. Do that in interval notation. Okay? If that's the case, if I'm just looking, and it's essentially looking at the unit circle, okay? It's just looking at that portion of the unit circle, right? Does that make sense to everybody? Okay? What are the only y values that you would pass through here? Negative 1 to 1. So our range is negative 1 to positive 1. And you're seeing that right here. If I put a y value of, let's just say A here, and ask to create a slider. We'll move this thing. Hold on a second. All right, so if I look at this slider here, the first y value I come through would be negative 1, right? And the last y value you pass through is positive 1, okay? If I looked at my x values, okay, the first x value you come through would be negative pi over 2, right? And the last x value you come through would be pi over 2, okay? So that's where we're seeing these domains and ranges come from, okay? Is everybody okay with that? So that thing then should have an inverse. It should have an inverse, okay? And the inverse from college algebra we talked about as being the reflection across what line? Yeah, line y equals x, okay? So, let's see here. All right, so this thing over here, and I'm going to make, just rewrite the domain was negative pi over 2, range, negative 1 to 1. And this is the sine function, okay? We want the inverse. So the inverse we're going to write as using that notation, sine inverse, okay? These ordered pairs should do what with one another? If they're reflections across the line y equals x. What should the coordinates of these ordered pairs do? So that one is pi over 2 comma 1. What should it become over here? Good. 1 comma pi over 2. Okay. This point right here is what is that? Pi over 3 comma root 3 over 2. So it should become root 3 over 2 comma pi over 3, right? Oh, I want that point to be over here. Okay. This point here, pi over 4, should now be square root of 2. If we flip-flop the x and y, square root of 2 comma pi over 4. This one here is pi over 6 comma 1/2, so it's going to be 1/2 comma pi over 6. We should have 0, 0 again. And you start to see kind of what happens with this curve. It's going to kind of do that behavior, right? Does that make sense? Okay, if we start plotting these points down here as well. So I'm just going to graph real quick the sine inverse of x. Okay, it's that curve right there. Okay, but like we said, with flip-flopping these ordered pairs, so this one was 1 comma pi over 2. This one was root 3 over 2 comma pi over 3. Now we flip-flop these. These were your x values. These were your y values. Over here, they flip-flopped, right? So what is the domain for the sine inverse? -1 to 1. Look at your x-axis. What are the x values that you're allowed to use? What x values is this graph being plotted for? It's only the x values between -1 and 1, right? Okay. Now your range values, your r values, or your y values, I guess, sorry. Your y values, you look here, it's a little bit less than -1.5, a little bit bigger than 1.5. And that's because my x-axis is not really labeled, or sorry, my y-axis is not really labeled real well here. Let's put this in terms of pi over 4. And you see, what is the first y value that you would come across here on this graph? -pi over 2. And your last one would be +pi over 2. And you see now that your domain has become your range, and your range has become your domain, right? Is that all right, everybody? Okay. So we're interested in looking at the sine function. Now, when we do this, and we use the sine function, there's some notation stuff that we need to kind of pay attention to. I guess I don't know if it's notation, but it's more like vocabulary. We can either call this like the sine inverse of x, kind of like that, or you might see it written that way. Okay, it's called the arcsine. Okay, and that's kind of like the old world way of writing it. With technology and ultimately a lot of the things that we do now currently with algebra by hand. The sine inverse, the one with the -1 as the superscript, it's not an exponent, it's a superscript. Is maybe a little more convenient, but when you take the ACT, you might every once in a while see them use arcsine or arctangent or arccotangent. They're just saying it's the same thing as sine inverse, cosine inverse, tangent inverse. Does that make sense, everybody? Okay. In calculus, that is actually arcsine. It's actually the preferred way of writing it in like a textbook. Okay. WebSign might every once in a while throw that in there. It'd be good to know. But they're saying the same thing. Okay. But you might get asked questions like this, or you will get asked questions like this. What is like the sine inverse? Let's just say 2. Okay. Sine inverse of 2. Now remember, this is a function, right? Sine inverse is a function. So this has got to be your input. Okay? And remember, your input is always your domain or your x values, right? Is there an issue here? look at my function. This is all my function, right? If I look at an input of x equaling 2, is there ever a y value that ends up on that line? No. Okay? So that's why when you take your calculator and you type in, let's see here, let's just clear this out. If I type in sine inverse of 2, that's why it tells me it's undefined. Okay? I just want to see something real quick. Arcsine. Awesome. I'll probably use that instead of sine inverse on this. We okay with that? So what if I put in 1/2? What if I put in 1/2? Okay. Sine inverse of 1/2. Now that is on my domain, right? So then sine inverse of 1/2, I'm asking what is the y value that is correlated with the x value of 1/2 on this curve? Well, that y value is what? Pi over 6. Okay? Sine inverse of 1/2 is pi over 6. So when I'm looking at my calculator, using my calculator, I say arcsine of 1/2. That's pi over 6. Okay? Convince yourself of that. Type in pi over 6, and it gives me that value, right? Does that make sense, everyone? Okay. So what is the logic that we're doing here? Right now, guys, what we're doing is if I look at just the sine curve, okay, I'm now asking you, if I give you the y value off this sine curve, could you tell me the x value that should be paired with it? Okay. Or, and it's the same logic, if we're looking at, let me open the unit circle up here. Okay, if I ask you to look at, this point right here, okay, and I tell you that I know that the y value I'm interested in is radical 3 over 2. Can you give me back that 60 degrees or that pi over 3 that's attached to radical 3 over 2? Does that make sense, everyone? Okay. Now, it's only going to work between pi over 2 and negative pi over 2, right? That set of quadrants are the only ones that we're looking at, okay? That being said, if I look at radical 3 over 2, is there a potential that I could actually be talking about 2 pi over 3 as an angle? Does that make sense, everybody? Okay? Because if we go back to, it might make more sense when we look at this. If I look at the line y equals, I'm going to say square root of 3 over 2. Doesn't that happen a lot of different places? Okay. My calculator is just going to give me that one right there, because my calculator is only being able to use the sine inverse using that restricted domain, right? We will have to do a little bit of algebra to find that answer, that answer, that answer, because those are all where the sine curve is equal to, or has a y value of radical 3 over 2, right? So we would be able to find that x value, that x value, that x value eventually, but it takes some work, okay? So in your homework, you guys are going to be asked questions kind of like this, where it says, can you guys, obviously do sine inverse of 1/2? What does that spit back? Well, it spits back 30, okay, or pi over 6. It's going to also ask you to do things like this. Can you take the sine of sine inverse of, let's say, radical 3 over 2? Okay, and I'm going to do this algebraically instead of using any shortcuts. I'm going to evaluate this, and these are nested functions, so we work inside out. So I'm going to evaluate that. If you remember, it's actually a composite function. Okay. If I look at sine inverse of radical 3 over 2, we're asking what is the angle measurement Okay, that should give me a y value of radical 3 over 2 off the unit circle. So sine inverse of radical 3 over 2. So radical 3 over 2, that's the input. What would be the y value that I get back here? Not, yeah, it's sorry, it's not the y value, it's the angle measurement. So that turns into pi over 3. Is that okay with everybody? Convince yourself of that. Okay, and it's really thinking of the unit circle kind of backwards now. Instead of basing it off of a radian and then getting the ordered pair, now we're going, okay, here's the ordered pair. Here's a coordinate in that ordered pair. Can you tell me the angle or the radian that goes with it? Okay, but if I go arc sine of square root of 3 divided by 2, gives me that, which Jarrett said was pi over 3, right? Okay, so we do get pi over 3. So now that thing, that inner function turns into or evaluates to pi over 3. And now I'm going to ask the question, because this sine is still on the outside, what's the sine of pi over 3? Radical 3 over 2. What happened with those two things ultimately? Cancel out. They are inverses, right? Addition, subtraction, multiplication, division, square roots, powers of 2, okay? Exponents and logarithms. Don't they undo each other? Because they're inverses, okay? Sine, inverse. They undo each other, okay? Now, the only thing you got to be careful with is sometimes we get questions, and I know we're going to run out of time here, but I might get a question like this. What about sine inverse of sine like this? I could put anything in here, okay? Because this is the sine function, and the sine function has a domain of all real numbers, right? Okay? So I can put anything I want in there, but whatever you put in there, my suggestion is to always bring it back down to something between 0 and 2 pi or 0 and 360. So for instance, let's do one in angle measurements in degrees. It might be a little bit easier. If I have sine inverse of sine of 390, doesn't it make a little bit more sense to do this? Is 30 coterminal with 390? Okay, now what's the sine of 30? 1/2. So now I'm going to ask you, what is sine inverse of 1/2? And that spits back what? 30. Okay? And if we ask Desmos, let's just see what it does. If I go arc sine of, what did I say, sine of 390. And now it's in radians, so let's change it back to degrees. You see that it does fit back that 30. My thought, you know, a lot of people say, well, sine inverse and sine, they cancel out, leaves me 390, right? It's not going to, okay? It's going to leave me 30. It's going to leave me the smallest possible coterminal angle that exists there, okay? Tomorrow, briefly, it'll be, I'll give you maybe 15, 20 minutes to work on that quiz over the 6 just parent functions. And we're not going to move them left, right, up, down, or anything like that. Just the parent function. I want you to know those points. Maybe later next week, early next week, I guess. Maybe I'll give you 2 or 3 to transform, but right now just concentrating on whether you know what those parent functions look like. Okay? So we'll do that tomorrow, and then we'll talk about this stuff a little bit more. Have a good day. Thank you, too.